Okay, we're going to be discussing the length of a polar curve. Now, I'm going to tell you that there's a little more to this, so there are some requirements to be met. So what we're going to say first is that, before I get into the formula, if r equals f of theta has a continuous first derivative for some theta between alpha and beta, and if the point r theta traces the curve r equals f theta exactly once as theta runs from alpha to beta, then the length of the curve is given by that formula there. L equals the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. All right, so we're just going to assume that the spiral that they give us here meets those conditions, and we're just going to find the length of the spiral. Right, it's really nothing to it. I think that you can get lost in the technical jargon of the definition, and the definition is important, don't get me wrong, but we're looking at this calculus in a filter because we know these problems are just going to work. All right, we just have to assume in this case that they just work. So what we're going to do is we're going to first note that we have to find dr d theta because we've already got r. So let's find dr d theta, and if you're confused about that, it's just r prime. So what is that? In this case, it's just 2 theta. All right, so we're going to use that because we need that in the computation of this. So we know that we're going to be going from let's see, where are we? From 0 to the square root of 5 because that's what was given. All right, so let's fill in what we know. The length L is going to be the integral from 0 to the square root of 5, and it's going to be the square root of r squared, which is theta square, plus dr d theta, which was our r prime, which we just said was 2 theta squared, and then d theta. Okay, so we have that, and it's not too difficult after this. It's going to be the integral again, 0 to square root of 5. We're going to have theta, and this was actually over here, theta squared squared. Let me clean that up. Theta squared squared. There we go. So this becomes theta to the 4th power plus 4 theta squared d theta. So now what we're going to do is we're going to try to simplify this root here, and it's very possible to do. All right, it is this integral from 0 to the square root of 5. Inside, we're going to factor out this square root, this theta squared to give us theta squared plus 4, and then d theta. And then this theta squared can be pulled out. So what does this look like? It is this integral of 0 to the square root of 5 of theta times the square root of theta squared plus 4. Now it's important to note that this is really the absolute value. We're only looking for the positive case here. We're talking about a length, of course. So we're talking about the length of this spiral that's colored here in purple, and we're going to figure out that value in just a minute. So again, we assume that theta is greater than or equal to 0. So in that assumption right there, we can drop the absolute value. All right, and what we're going to do is we're going to do some u substitution now, and that was the whole point of breaking it up, so we could do a u substitution here. So we're going to have theta squared plus 4 on the inside of that radicand, but we're going to say, okay, let's assume u equals theta squared plus 4. What is du? Well, it's 2 theta d theta. Well, I've got the theta d theta. What am I missing? I'm missing the 2. So by consequence, so I write the 2, I make it happen. By consequence, I need to write a 1/2 on the outside. And so let's go ahead and put a ring around this stuff. This right here represents my du, and this right here represents my u. Now I can go ahead and adjust the limits of integration to make this a lot easier. 0 to the square root of 5. So on my u, if I plug in 0, I get 0 squared plus 4, which is 4. And square root of 5 squared is 5 plus 4, which is 9. So we're going to integrate now from 4 to 9, and this makes this problem so much easier. Once we've adjusted the limits of integration, we have a 1/2 sitting on the outside. we have an integral from now 4 to 9 of u to the 1/2 power, because it's the square root, du. So what does this look like? Well, this is 1/2 u to the 3 over 2, because you add 1 to the exponent, and then you divide by 3 over 2. All right? But as I always tell my students, remember to KFC. So again, we're evaluating from 4 to 9. All right, so here we have, let's see, 1/2 times 3 over 2 becomes 2 over 3 times 1 over 2. The 2's cross out. U to the 3/2 from 4 to 9. All right, so let's see what this looks like. This is a 1/3 of u to the 3 over 2 evaluated from 4 to 9. All right, and there's really not much more to this after that, because it's pretty straightforward. We're going to have a 1/3 on the outside. I'm going to write u, in this case 9, and I'm going to take the square root. So let me write that as the square root of 9, and then I'm going to write it as the square root of 9 cubed. Square root of 9 cubed minus a square root of 4 cubed. All right, so that's how we would set that one up as well. All right, so we know that we can take the square root very easily. We have 1/3, and the square root of 9 is just 3 to the 3rd, minus the square root of 4, which is just 2 to the 3rd. And we know these values very simply. Okay, 3 cubed, of course, is 27, and 2 cubed, of course, is 8. 27 minus 8 is 19, and so we have 1/3 times 19, bringing our final answer here, the length of the spiral, to be 19 over 3 units. And that right there is how you would compute it. Again, really nothing to it. Yes, there's some calculus involved, but it's not that bad. It's actually perfectly okay. All right, you apply the formula and you can get the length of that polar curve, and that's how you'd go about approaching this. As always, I hope this video was helpful, and remember, like and subscribe.